Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 2, Section 2, Chapter 3, Topic 4. Understanding S-parameters and Time Domain Reflectometry, TDR, for Signal Integrity Analysis. Introduction. In the realm of signal integrity analysis, accurate characterization of transmission lines and interconnects is essential for evaluating signal behavior, mitigating signal degradation, and optimizing system performance. Two commonly used techniques for assessing transmission line characteristics are frequency domain S-parameters analysis and time domain reflectometry, TDR. This overview explores how these techniques are used to measure loss, crosstalk behaviors, and impedance reflections in transmission lines, providing insights into their applications and benefits in signal integrity analysis. Frequency domain S-parameters analysis. 1. Definition and significance. S-parameters, or scattering parameters, are complex valued coefficients that describe the behavior of a linear electrical network in the frequency domain. S-parameters quantify how signals are transmitted, reflected, and coupled between different ports of a network, providing valuable insights into transmission line characteristics such as loss, crosstalk, and impedance matching. 2. Measurement setup. S-parameter measurements involve applying stimulus signals to the network under test, NUT, and measuring the reflected and transmitted signals at various frequencies using a vector network analyzer, VNA. The VNA injects signals into the NUT through one port while measuring the incident, reflected, and transmitted signals at all ports simultaneously, allowing for the determination of S-parameter values across a wide frequency range. 3. Loss and crosstalk analysis. S-parameters provide valuable information about loss and crosstalk behaviors in transmission lines. Loss is characterized by the magnitude of S-parameters, with higher magnitudes indicating greater signal attenuation. Crosstalk is characterized by the coupling terms in the S-parameter matrix, representing the amount of unwanted signal coupling between different transmission lines. 4. Impedance and reflection analysis. S-parameters also provide insights into impedance and reflection characteristics of transmission lines. The real part of the S-parameter matrix represents the impedance of the network at each frequency, while the imaginary part represents the reflection coefficient, indicating the amount of signal reflected back from the network. Time domain reflectometry, TDR. 1. Definition and significance. Time domain reflectometry, TDR, is a measurement technique used to analyze the impedance, reflections, and discontinuities in transmission lines in the time domain. TDR sends short electrical pulses into the transmission line and measures the reflections caused by impedance variations, discontinuities, and faults along the line. 2. Measurement setup. TDR measurements involve applying a fast rise time pulse to one end of the transmission line and capturing the reflected signals using a sampling oscilloscope. The time delay and magnitude of the reflected signals provide information about the impedance, reflections, and discontinuities in the transmission line. 3. Loss and impedance analysis. TDR measurements allow for the characterization of loss and impedance variations along the transmission line. Loss is quantified by the amplitude of the reflected signals, with higher amplitudes indicating greater signal attenuation. Impedance variations are identified by changes in the time delay and slope of the reflected signals, indicating impedance mismatches or discontinuities. 4. Crosstalk analysis. TDR can also be used to analyze crosstalk between adjacent transmission lines. By measuring the time delay and magnitude of crosstalk signals, TDR provides insights into the coupling between different transmission lines and helps identify potential crosstalk issues. Applications and benefits. 1. Signal integrity analysis. S-parameters and TDR are widely used in signal integrity analysis to characterize transmission lines, identify signal degradation issues, and optimize system performance. By measuring loss, crosstalk, impedance, and reflections, these techniques provide valuable insights into the behavior of transmission lines and help designers ensure reliable signal transmission in electronic systems. 2. High-speed digital design. In high-speed digital design, S-parameters and TDR are used to evaluate the performance of high-speed interconnects, analyze signal integrity issues such as signal attenuation and impedance mismatches, and optimize the design for minimal signal degradation and crosstalk. 3. PCB and interconnect design. S-parameters and TDR are essential tools for PCB and interconnect design, allowing designers to characterize transmission line properties, validate design assumptions, and identify potential signal integrity problems early in the design process. Conclusion. Frequency domain S-parameters analysis and time domain reflectometry (TDR) are valuable techniques for measuring loss, crosstalk behaviors, and impedance reflections in transmission lines. By providing insights into transmission line characteristics in both frequency and time domains, these techniques enable designers to evaluate signal integrity, identify potential signal degradation issues, and optimize system performance. Incorporating S-parameters and TDR measurements into signal integrity analysis helps ensure reliable signal transmission in electronic systems, making them indispensable tools for high-speed digital design, PCB design, and interconnect optimization. Thanks for watching. Please like, share, and subscribe.